Okay, so we're continuing with chapter 6. Whoa, what the? Continuing with chapter 6, and we're looking at how halogens, Br2 and Cl2, can interact with an alkene. And we've examined using solvents of CH2Cl2, which has no effect, no reaction. We've examined the solvent of water, which does have an effect. If we have a halogen plus water, then we form halohydrin as our final product, OH group and halide group on the final molecule. But we can use other solvents besides water as well. So let's look at a couple of other nucleophiles in addition to water. First, methanol. So when we have a nucleophile other than water, we still have to know that the intermediate is the halonium ion. So this is where we form this is the halonium ion that would be formed from the alkene given. Here's our halonium ion that would form. And then we have to evaluate what are our possible bases. We know that when we add chlorine to the pi bond, we also form chloride ion. And so we have to compare chloride ion and the solvent methanol for basicity. In order to determine which is a stronger base, we should first look at which is a stronger acid. So the conjugate acid of chloride ion is HCl, has a pKa of -6, and the conjugate acid of methanol is protonated methanol, which has a pKa of +2. Now we apply our rule of strong conjugate acid, weaker conjugate base. So since HCl is the stronger acid, the protonated methanol will have the stronger conjugate base. So protonated alcohol has a stronger conjugate base, then methanol is a stronger base than chloride ion. And that means that methanol will preferentially act as the nucleophile over chloride ion. And that is why in the final product, it's the methanol molecule that adds through its lone pair to the, I'm sorry, I need to redraw the arrow. It's the methanol ion that adds through its lone pair to the halonium ion, and the methanol molecule is going to add at the more substituted carbon and break the three-membered ring. And that will give us chloride at the less substituted carbon and the what we call a methoxy group at the more substituted carbon. So when we use an alcohol as a solvent, that results in an ether functional group being added. In the second case, we have bromide and NaCl. So we have our solution with one equivalent of alkene, one equivalent of Br2, and this is all dissolved in aqueous sodium chloride. So sodium chloride is present in excess of bromine. When the bromine reacts with the alkene, our first step is to form our halonium ion. So we have a 3-carbon molecule, 1, 2, 3. We form our halonium ion intermediate, and then we have to decide what is our base. What are our options? When Br2 reacts with the alkene to form the halonium ion intermediate. It also produces bromide ion. We have bromide ion and we have chloride ion. Chloride ion is present in excess of bromide because it is the solvent. So the solvent is always present in excess. And between the two options, we should evaluate which is a stronger base, bromide or chloride. The base is going to end up at the more substituted carbon, and the halogen, the Br2Cl2, the atom that is represented by those halogens always ends up at the less substituted carbon. So looking at bromide and chloride being our options, we're going to look at the acids first, and then based on which is a stronger acid, we'll know which is a stronger base. So when we compare HBr and HCl, we know that when we go down a group, acidity increases. That means that HBr is a stronger acid than HCl. Stronger acid will have a weaker conjugate base. So bromide ion is a weaker base than chloride ion. Our stronger base, chloride, is what will add at carbon 2 to break the three-membered ring halonium ion. And that will result in the final product having a chloride at carbon 2 and a bromide at carbon 1. So that the halogen represented by Br2 or Cl2, whichever you use, always ends up on the less substituted pi carbon, and the halogen that is acting as the base is always going to end up on the more substituted carbon, or the solvent that acts as the base ends up on the more substituted pi carbon. So this gives us as our final product 1-bromo-2-chloropropane. Now, I want to point out something here that we are going to discuss in detail later. When we perform this reaction, we have now generated an asymmetric center. When we perform a reaction that generates an asymmetric center, this is the product will always be a racemic mixture of enantiomers. So our four different groups for our new asymmetric center that occurs at carbon 2 are methyl, chlorine, and bromomethyl group. So we have, for our four groups for our asymmetric center, 1, chlorine, 2 is the CH2Br group, 3 is the methyl group, and 4 is hydrogen. So you can see that we've made a new asymmetric center, and that is going to affect how we draw the final product, because in some cases they ask for all possible isomers, and when they ask for all possible isomers, that usually indicates that from the reactant to the product has an additional asymmetric center that the reactant did not have. Okay, our next reaction, we're no longer dealing with reactions of Cl2 and Br2 with alkenes. Now we're going to look at the addition of a peroxyacid to an alkene. This is number 8 on your functional group notebook, the formation of an epoxide. Okay, so when we have a peroxyacid, you must first be able to recognize what a peroxyacid is. So if you look at the molecules, we have as our reactants alkene, peroxyacid makes an epoxide and a carboxylic acid. So if you look at this peroxyacid, what you see is that instead of a normal carboxylic acid, we have 2 oxygens coming off of the carbon before we get to the hydrogen. So a peroxyacid should have the formula it should have the formula CO3H. So instead of a carboxylic acid, which has CO2H, a peroxyacid has the general formula of CO3H. Okay? And what is physically happening to form the product of the epoxide is shown below. So we have our peroxyacid, oxygen, single bond hydrogen, and our alkene. The alkene pi electrons are nucleophilic, and they are going to bond to the oxygen that is bonded to hydrogen. The sigma bonding electrons between the oxygen and the hydrogen are going to go and be donated to make a bond to the less substituted pi carbon. So the pi bond, the pi electrons go from the more substituted pi carbon to the oxygen, and the sigma electrons between oxygen and hydrogen go into making a bond to the less substituted pi carbon. Simultaneously, the sigma electrons between the 2 single bonded oxygen, the 2 sp3 oxygens, go to making a pi bond to carbon, between carbon and oxygen. So we have C double bond O. And then the pi bond that existed between carbon and oxygen go into making a single bond to hydrogen. And that gives us, and these 4 arrows all occur simultaneously. And what that does is it gives us a carboxylic acid. Notice I have color coordinated, so the arrows showing the electrons of this sigma bond are going to make a pi bond here. Here's the corresponding pi bond drawn, highlighted in purple. The arrows of the the pi bond that existed in the original peroxyacid, showing in blue that those electrons are going to hydrogen, and we have highlighted the corresponding oxygen to hydrogen bond in blue in the product. And then we show that in the formation of the epoxide, which should look like this, it should be more clearly that the CH2 is at this position. You can see how the pi electrons from the pi bond indicate movement of the light blue arrow to the oxygen, and that is shown in the highlight of where those electrons are going to. So we've made a sigma bond to oxygen with these electrons. And then we have the sigma electrons in the peroxyacid from O to H, showing in green that those are going to make a bond to this carbon here. And that is the mechanism for the peroxyacid. I recommend that you fill out your functional group notebook as we go through this reaction. We're going to go look at the, we have more information on this, and then we have your book's depiction of the mechanism. So an oxygen-oxygen single bond is a very weak bond. And that is because both of the oxygens are electron withdrawing. So they don't want to share those electrons. The most common peroxyacid that we use is MCPBA. That's how the ACS test writes it out. That's how you'll see it on my exams. Now, on exams and in your text, sometimes they will give you the structure and you will have to know the name. You'll have to know that it's an MCPBA, or at the very least recognize the functional group. Now, this is just the most common one. But even if your book gives you a generic peroxyacid as a reagent in a reaction, you should know that the product will be the epoxide. So they may give you a specific reagent, or they may give you that you have a very general peroxyacid, and you should still know what the product of that reaction will be. And they may not give you, but the problem is that they also may not give you the molecule at all. They may just give you the acronym MCPBA, and then you have to know, well, what is MCPBA? It's called it then, and it might help to understand what MCPBA stands for. So MCPBA stands for meta chloro peroxy benzoic acid. So this is a peroxyacid, peroxybenzoic acid, as the name indicates. And so if you know what the letters stand for, that will help remind you that it's a peroxyacid and what the peroxyacids do as a reagent. Now, in Chapter 8, we'll learn what the prefix meta means. Meta is simply a way to describe the relative positions on the ring. When we use the term meta, that is describing that there are two substituents on the ring, and relative to one another, they are in a 1-3 position. So one of the two groups is at position 1, and the second group is at position 3. And position 1 is always assigned to the higher priority functional group, and that would be the peroxyacid. Okay. Mechanism for epoxidation. This is required in your functional group notebook. So you can see we can highlight where the electrons are moving from and to. We have our pi electrons. Whoops. You know, I am going to do this. Whoa. Outside of presenter view. And keep. Select. Okay. So we can use our highlighter. These, whoa. All right, so this pi electron here is going to the oxygen on this side according to this arrow. Okay, and then this bond, according to this arrow, is going to the other pi carbon. So here's our new, that's where those electrons went. And then we have our sigma electrons from O to O going to make this pi bond here. And we have our pi electrons from C to O going to make a bond to hydrogen. And that's where those electrons move to. So you can color coordinate and help yourself see the final picture using colors. This is the same mechanism that I showed previously. These arrows are consecutive, are not consecutive, they're simultaneous. So they don't happen one after another, they all happen at the same time. Okay? And it's similar to the mechanism of the halogenation of an alkene, but it is not identical. The biggest similarity is the formation of the three-membered ring to the heteroatom. And what does heteroatom mean? Not carbon or hydrogen. Any atom that is not carbon or hydrogen.